Hello, I'm going to do a problem for you. I'm going to do problem, let's see, it's 1.5, number 7. So what we are trying to do here is we're trying to solve this differential equation. So the differential equation is 2x y prime plus y. We want that to be equal to 10 times the square root of x. Okay, so the first thing we can see here, let me just write down some things that we have to have. We know that we know that x is going to be greater than 0. Greater than or equal to 0 in this discussion because we're taking the square root of it. This will, as you will see, will simplify our calculations. Okay, so the way we're going to do this is we're going to first turn this into a first order linear equation, or a linear first order equation, however you prefer to say it. And so we're going to divide both sides of this equation by 2x, which leads us to this new differential equation. We want y prime plus, I'm going to write it this way. I'm going to write it as 1 divided by 2x y. That must be equal to, and I'm going to use sort of modern notation. So I'm going to write that as 5x to the, it'll turn to negative 1/2. Divide both sides by x, that's what you get. Okay, now the idea of this integrating factor is first thing you need to do, I guess I'll do this in blue, kind of to that'll make it look more interesting, I guess, so I can change the color. What I'm going to do next is I'm going to actually integrate this thing right here, and it's in blue, okay? I'm going to find a definite integral of that. So what I'm going to do is I'm going to find the integral from, I'm going to choose from 1 to x, but now I'm going to integrate 1 over 2t dt. Okay? So when if you integrate this by the fundamental theorem of calculus, you can see that what you get is, well, essentially you're going to evaluate from 1 to x, and then let's see, an antiderivative of this 1 over 2t is actually just the natural logarithm of t divided by 2. Okay? So now when you if you evaluate that, we get this function, just a natural logarithm of x divided by 2, okay, which we can rewrite as the natural logarithm of x to the 1/2 power. Okay. So now the idea of the principle of this integrating factor is that we take this function and we exponentiate it. So we're gonna find essentially e to the natural logarithm of x to the 1/2. And since these are inverses of each other, the function logarithm and the exponential, we just get x to the 1/2. Okay. Now what we do is we're going to multiply our differential equation by this differential equation here, the one that we just found here, by our x to the 1/2 on both sides. And if we do that, what we see that we get the following. We get x, well, here I'll go back to black, I guess, why not? I don't know why it's that critical, but I'm going to just do it anyway. Okay, it's in very dark blue, evidently. So if we multiply both sides of that equation by this quantity, the equation I'm speaking of is this here. I'll cut, well, this is y prime. Okay, I got it. Then we get the following equation. We get x, you get x to the 1/2 y prime plus then we actually get, it's going to be, let's see, let me go back up there. Notice how this term we have this 1 over 2x, so I'm going to get a 1/2 is still going to remain there. So I'm going to get 1/2 y, but now I'm going to get actually an x to the minus 1/2. Is that correct? Let me think. Yes, because there was an x in the denominator, so now there's an x to the minus 1/2. And that will be equal to, well, let's see, we had 5 times x to the minus 1/2, so if I multiply by x to the 1/2, we just are left with 5. Now the reason this works is the following. If you look at the left-hand side of this equation, what you're looking at is the derivative with respect to x of, see, this is really, we're looking at the product rule of something here. And let's see what this is. Well, it's actually, if you look at it, it's x to the 1/2 times y. I'll show you this. Let me show you. You may, I hope, remember from calculus the product rule, right? Let's confirm that this is in fact correct. Like, if I were to differentiate this thing, let's make sure we get this. Well, let's see. We get the first function right here, which is this x to the 1/2, times the derivative of y, which is right here, plus the derivative of x to the 1/2, which is 1/2, oops, x to the minus 1/2. It's right, well, sort of here. That's split up, but that's fine. And then times y, that's equal to, that's the thing. Now that we know that we're looking at the derivative of some function being equal to 5, we can easily find out, well, we can anti-differentiate both sides, so I'll do that by just putting a, what color do we like here? A little red antiderivative thing there. So the antiderivative of this function with respect to x has to be the same as the antiderivative of 5 with respect to x. And that's where we get our formula or our solution from. Because when you anti-differentiate a derivative, you just get the object back again. Here, so I'm going to write down. So this is x to the 1/2 y, and this is equal to 5x. And now I have to throw a constant in there, because when you integrate, you get a class of functions. So I put all the constants on the right-hand side of the equation. And now when I divide through by x to the 1/2, I get that y has to be equal to 5. Now this turns out to be just x to the 1/2 plus the constant times x to the minus 1/2. So there's an example of how to solve an equation using this integrating factor. So thank you very much.